Alright, this video is going to be on inverses of functions, and to start we're just going to look at inverses of graphs because I think that's a good starting point when you're drawing things. So here's the first graph we're going to look at. If you can see this dotted line right here, and if you try to write the equation for it, you'll notice that it's a slanted line, so we would write it in y equals mx plus b form. And it goes through 0 as a y-intercept. So that means that the plus b part would be plus 0. And if you can see, it has a slope of up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. And so that means the slope is 1 over 1. And then I can fill in the rest. Now here, we wouldn't normally write 1 over 1x. We would just say that's x. And we wouldn't normally put a 0. We would just say there's no number there, so don't write it. So that's actually the equation of the line, y equals x. That's the equation. And the dashed line, it goes straight through 0, has a slope of 1. So when you are finding the inverse of a graph, you actually take the points and you reflect them over that dotted line. And this reflection is not going up. You're not going, or down, I guess. You're not going down and going across the x-axis. You're not going across the y-axis and going to the right. You're going across the line y equals x, which is a diagonal line. So when you reflect these points, you can't think of reflecting them left and right or up and down. You have to think about reflecting them diagonally. So if I start with this point here, and I want to reflect it across the dashed line, I'm just going to count and see how many boxes away from the line it is. So I can count 1 diagonal box, 2 diagonal box, 3 diagonal boxes. And then I'll go ahead and keep going. So 1 box, 2 box, 3 boxes across, and there's my point. For this one, I've got 1, 2 boxes, and so I'll count 1, 2 on the other side, and put my point. And then I've got 1, 2, 3, 4 boxes, and I'll count 1, 2, 3, 4 boxes and put my dot. Alright, and technically I shouldn't have had these little lines here. So you can go ahead and erase those if you drew them. If you drew them in pen, you don't scribble it out, just don't worry about it. And so here's the inverse. And I can see it. It was reflected over that line. Alright, so let's do this with number 3. So I'm going to go ahead and count. This one goes 1, 2, 3, 4 and a half. So I'll count, there's the half, and then 1, 2, 3, 4. This one's on the wrong side of the line, so we're going to go ahead and reflect it. We're just going to reflect it on the other side. So this looks like it's 1 and a half. And so there's the half, there's 1. And then we'll do the last one. We got 1, 2 and a half again. So half, 1, 2. I'm going to go ahead and erase my little counting lines. So here is my inverse. And then what I would like for you to do is I'd like for you to pause the video and look at number 5. It says to write down the coordinates of the original, so write down the coordinates of the black line and see what those coordinates are in these 3 spots, and then write down the coordinates of the inverse, so the red ones, and see what you notice, because you will notice something. There's definitely a pattern to these. All right, and then once you unpause the video, we're going to go ahead and skip page 2. Sorry about that. And we're moving on to page 3. So at the top of page 3 it says, what are inverse operations? So if you recall, operations are like plus, minus, multiply, divide. And so inverse operations are operations that are that undo each other. So if I start off with addition, the operation that undoes addition is subtraction. If I think of multiplication, the operation that undoes multiplication is division. If I think of square rooting something, the operation that undoes that is a little squared. The little exponent of 2 would undo a square root. So those are some inverse operations that are common that we have dealt with in the past. All right, next your notes are asking about the notation for inverse functions. And here that's a small blank, but we actually have 2 different types of notation, so I'm going to write both of them down. So sometimes we're going to have equations that say y equals, and sometimes we're going to have equations that say f of x equals. And the notation for the inverse function is slightly different depending on which one they give you. So if they give you y, then the inverse would be written as, the inverse would be written as y inverse, like that. So if the original equation has a y, then your inverse should say y equals, but y inverse. If your original has the function notation f of x, then you're going to write f inverse of x. So your notation is going to match the original problem. Now I want you guys to be able to say this out loud if you're like reading me a problem. So this is y inverse, that's how you pronounce it. And for this one, you would say f inverse of x. F inverse of x. Alright, so this next part is kind of like the answer for number 5 on the previous page. How can you find the inverse of a function without having to graph it first? And the answer is you can trade the x and the y value. So if you take a point and you reflect it over the line y equals x, you're actually taking the x and the y values and you're trading them. So you can do that with a graph, you can do that with a table, you can do that with points, you can do that with an equation. Anytime you find an inverse, all you're going to do is trade the x and the y value. So here, in this example, they said f of x equals 4x plus 3, and they want us to find the inverse, and they want us to do it without graphing. So for me to do that, I'm going to go ahead and scribble out this f of x, and I'm just going to say that's the y coordinate. I know that my final answer should have this inverse notation, but it's easier for me to trade x and y if I actually have a y in the problem. So I'm going to go ahead and write y right there. So my first step to be able to make this an inverse is to trade the x and the y. So I'm going to say I have x equals 4y plus 3. Now what I need to do from here is I need to undo each of these operations. And I'll do that by taking the inverse of each of them. And when I'm finished with that, then I'll have my equation in y equals form, which is how we usually like our equations to be written. So the inverse operation for plus 3 is to subtract 3. So that's where I'll start. I have x subtract 3 equals 4y. And the inverse operation for 4 being multiplied by something is to divide by 4. So I'll go ahead and divide by 4. So now I have isolated the y value by doing the inverse of each operation, and that means I have found the inverse function, and I can go ahead and just rewrite it with that inverse notation. So for this one I would say f inverse of x equals x minus 3 over 4. And that would be the inverse function. So if you can tell, looking at the original function in this inverse, each operation has been undone. The plus 3 has been undone, we got a minus 3. The multiply by 4 has been undone, we have a divide by 4. Alright. Inverse functions are reflected over the line y equals x. What happens to the coordinates when they are reflected over this line? It's normally written as xy, and then after they're reflected over the line, they become yx. So we're going to say the x and y values trade. Next, it asks us how can you test to see if the function you found is indeed the inverse of the original function, we have two things we're talking about. One is a relation. That's just talking about a pattern with numbers that have a relationship to each other. If you flip to the top of the next page, you'll actually see an example of a relation right here. That's a relation. So we're going to look at one of those in a minute. But when you look at a relation, the way that you will test to see if it's actually inverses is you will just check to see that all points x, y have become yx. So you'll just make sure that every single point, the x and the y coordinate have switched. In a function, if we want to check to see if the new function is indeed the inverse of the original, for a function we will compose the two functions. And we have two ways of composing them. One is we can say f of the inverse function. So we can take the inverse function and plug it into the original function. Or we can take the original function and plug it into the inverse function. And what will happen when we do this is we have all these operations that are undoing each other, right? So the plus 3 and the minus 3 would cancel out, and the multiply by 4 and the divide by 4 would cancel out. And when that happens, all the numbers in the problem will have canceled out, and this composition will simplify to just be x. So anytime you compose two functions and your final answer is just a plain old x all by itself, that means that those two functions were in fact inverses of each other. So you can do this test when you just take two random functions and test to see if they're inverses, or if you're doing a problem where you have found the inverse and you want to check your answer, then you can use composition to check to see if you did it correctly. All right, so on the next page we're going to do a couple examples of these. So find the inverse of each relation or function. So here we have f is 1, 3, 1, negative 1, 1, negative 3, 1, 1. So for the inverse, I'm going to go ahead and switch all of those. So this one would be 3, 1, negative 1, positive 1, negative 3, positive 1, and then positive 1, positive 1. All right, down here, so we have g of x equals 2x minus 1. If I want to find the inverse function, first of all, I'm going to go ahead and take this g of x and write y instead. And the first step is to always trade the x and the y value. So x equals 2y minus 1 divided by 3. And then as we go about the problem and we start to get y all by itself, we are doing inverse operations as we do that. And so that means we're going to find the inverse function at the very end of that process. So here, my first inverse operation is to multiply by 3 to cancel out that divide by 3. So I'm going to multiply by 3 right there. I have 3x equals 2y minus 1. The next inverse operation that I can do is I can add 1 to each side. So I have 3x plus 1 equals 2y. And then at the very end, I can go ahead and divide each side by 2. So divide by 2, divide by 2, and that leaves me with y equals 3x plus 1 all divided by 2. And I can see that all of these operations have been undone. There's a divide by 3, and I've got a multiply by 3. There's a minus 1, I've got a plus 1. There's a multiply by 2, I've got a divide by 2. So here my original function was g of x. Now my inverse function is going to be g inverse of x. And then I can go ahead and just write what I had. All right, for this next one, again, I'm going to scribble out this g. I can see that that should be a y, and then I'll go ahead and trade my x and my y. So x equals y plus 2 squared minus 3. And I'm going to go ahead and undo each operation. So the first one that I can undo is that 3. I can go ahead and add 3 to the other side. So x plus 3 equals y plus 2 squared. And then I can undo that squared by square rooting each side. So now I have the square root of x plus 3 equals y plus 2. Now because we did a square root to get this answer, anytime you square root as part of doing a problem, you have to put a plus or a minus in front of that. Plus or minus. Okay. And now to finish this, we have to subtract 2. And that subtract 2 does not go with the 3. The 3 is protected by that square root sign. That minus 2 is actually on the end of the problem. So I'm going to say this is y equals plus or minus square root of x plus 3 with a subtract 2 on the end. And I'm going to go ahead and fix my notation. So this is g inverse of x equals plus or minus the square root of x plus 3 with a minus 2 on the end. Alright, and then last, I apologize for how long the video is. Last, they're asking us to use composition to determine if the functions are inverses of each other. And so that means you just need to put one into the other. It does not matter which one. So put one function into the other, it does not matter which one. So I'm going to go ahead and let f be the outside function and have g be the inside function. So that means I'm going to say f of x equals 2 times x minus 3. And I am plugging in g of x. And I'll go ahead and plug in g of x, negative 2x plus 3. And if these are inverse functions, then all of the operations will cancel each other out. And my final simplification for this problem will be that it's just equal to x. That's it. So to simplify this, I'm going to go ahead and get rid of my parentheses by distributing. And I get negative 4x plus 6 minus 3. So that minus 3 was from the end. And that gives me negative 4x plus 3. And so this is not an inverse function. These two are not inverses of each other. It left the expression negative 4x plus 3. Alright, and that's going to be it for our inverse function notes.